flux is fundamentally governed by Fourier's law of heat conduction. This law states that heat flux is proportional to negative gradient of temperature. In simpler terms, heat flows from hotter regions to colder regions, and the rate of heat flow is greater for steeper temperature differences. So Qx is directly proportional to minus dou T by dou x, Qy to minus dou T by dou y, and Qz to minus dou T by dou z. Where T is the temperature, the proportionality constant is the thermal conductivity of the fluid. Therefore, the conductive heat flux vector Q represents the rate at which thermal energy is being transported through the fluid due to these molecular interactions driven by temperature differences. Even if the bulk fluid is not moving, heat can still be transferred from a hot part to a cold part through conduction. Imagine you are placing a metal spoon in a hot cup of coffee. Even if the coffee itself isn't swirling, the heat from the coffee will travel up the spoon through conduction due to the vibrations and collisions of the metal atoms. Similarly, within the fluid with a temperature gradient, heat will be conducted from a higher temperature regions to lower temperature regions. Now that we have examined three fundamental modes of energy transport, convection, work due to molecular motions, and conduction, we can understand how they combine to give the combined energy flux vector E. Now we'll find an expression for the x component of this vector Ex as a part of total energy flux vector tau dot V plus PV plus Q. Expanding this and considering the convective term derived earlier, we can see the combined energy flux accounts for energy carried by bulk motion of the fluid. This includes the internal energy and kinetic energy as well as the work done by pressure forces represented by terms involving the velocity components Vx, Vy, Vz and pressure P. Energy transfer due to viscous stresses. This is represented by terms involving the shear stress components tau xx, tau yx, tau zx and their y and z counterparts multiplied by the corresponding velocity components. As mentioned earlier, this accounts for the work done by these stresses. Energy transfer due to heat conduction. This is represented by the components of heat flux vector Qx, Qy, Qz. Now we have the total energy flux vector, which includes the terms like tau xx into Vx plus tau yx into Vy plus tau zx into Vz, which is the rate of work done per unit area due to viscous stresses. When we consider combined energy flux vector, its x component Ex can be expressed more fully as Ex is equal to rho into E plus half V square plus P into Vx plus tau xx into Vx plus tau yx into Vy plus tau zx into Vx plus Qx. Similarly, Ey and Ez would have analogous forms involving Vy and Vz, the corresponding shear stress components, and Qy, Qz. In this specific case, we have Vx is equal to 0 and Vy is equal to 0. The x component will simplify to Ex is equal to tau zx into Vz plus Qx, and further, using a constitutive relation for viscous stresses, tau zx is equal to minus mu into dou Vz upon dou z, and Fourier's law Qz is equal to minus k dou T by dou x, leading to Ex is equal to minus mu dou Vz upon dou z into Vz minus k into dou T by dou x, where mu is the viscosity and k is the thermal conductivity. Therefore, the combined energy flux vector provides a comprehensive picture of how energy is being transported in a fluid, taking into account both bulk motion and the molecular level interactions. The concept of energy flux is a fundamental where we perform energy balance and control volume or a shell within a flowing fluid. The shell energy balance equation presented states that the rate of combined energy flux in minus the rate of combined energy flux out plus the rate of work done on the system by external forces plus the rate of energy production equals 0. One important application is the phenomenon of viscous heating. As discussed earlier, work done by viscous stresses can lead to dissipation of mechanical energy into thermal energy, effectively acting as a heat source within the fluid. It is also mentioned that the rate at which work is done is the force acting on a moving plate times its velocity. When considering the fluid between moving surfaces, the viscous dissipation becomes significant and is represented by a volume heat source term SV, which appears naturally in the energy balance when using the combined energy flux vector. Now we consider some specific examples such as flow of an incompressible Newtonian fluid between coaxial cylinders. In such cases, the rotation of one cylinder relative to the other causes viscous dissipation within the fluid, leading to a temperature profile that is influenced not only by the boundary temperatures but also by this internal heat generation. The combined energy flux equation is crucial in deriving the temperature profile under such circumstances. The Brickman number Br mentioned is a dimensionless parameter that quantifies the importance of viscous dissipation term relative to heat conduction. In conclusion, the combined energy flux equation provides a powerful tool for analyzing energy transport in moving fluids by encompassing convective transport, energy transfer due to viscous stresses, and conductive heat flux. It allows us to develop comprehensive energy balance equations for various fluid flow scenarios, including those where viscous heating plays a significant role. Understanding each component of combined energy flux is essential for tackling complex problems in heat transfer and fluid mechanics.
Hello everyone. Now we are going to discuss about the boundary conditions. Here we are considering a tubular fixed bed reactor, a common type of reactor in chemical engineering where solid catalyst particles are packed in a tube and a fluid reactant mixture flows through this bed undergoing a chemical transformation. The heat generated or consumed by this reaction significantly impacts the temperature profile within the reactor, which in turn can affect the reaction rate and selectivity. We conceptually divides this reactor along its axial direction, denoted as Z, into three distinct zones. Zone 1, the entrance zone. This section extends from the inlet where Z approaches negative infinity up to Z equals to 0. Crucially, in this zone, the packing consists of inert spheres. This means these spheres do not catalyze the primary chemical reaction of interest. Consequently, there is no internal heat generation or consumption due to the main reaction occurring within this section. However, there might still be heat exchange between the fluid and the inert packing material. The purpose of this zone might be for preheating or achieving a certain flow profile before the reaction zone. Now zone 2, the catalytic reaction zone. This is the heart of our reactor, spanning from Z equals to 0 to Z equals L. Here the packing is made up of catalytic spheres. This is where the intended chemical reaction takes place, and as a result, this zone is characterized by a significant source or sink of thermal energy, represented by the term S in our equations. The magnitude and sign of S will depend on the reaction kinetics and whether the reaction is exothermic, releasing heat S greater than 0, or endothermic, absorbing heat S less than 0. The length L of this zone is a critical design parameter influencing the overall conversion and temperature control. Now, Zone 3, the exit zone, similar to Zone 1. This section is packed with non-catalytic or inert spheres and extends from Z equals L to Z approaching positive infinity. Again, no significant heat generation or consumption from the primary reaction is expected here. This zone might serve to cool down the product stream or to ensure a more uniform temperature profile at the reactor outlet. It's vital to understand the spatial arrangement of these zones. They are sequential along the axial length of the reactor. The fluid stream first enters zone 1, then flows into zone 2, where the reaction occurs, and finally exits through zone 3. So now that we have a clearer picture of the physical setup, Let's delve into the mathematical description of heat transfer within the system. Our sources provided us with differential equations that mathematically represent how the temperature, often denoted as T, varies as a function of the axial position Z. These equations are derived based on fundamental energy balance principles applied to a small control volume within each zone. In this particular analysis of a fixed bed reactor, several simplifying assumptions are often made, like the velocity is well developed, meaning the flow profile is not changing significantly along the axial direction. Furthermore, it is often assumed that the temperature is essentially uniform in radial direction. This is a significant simplification that allows us to treat the problem as one dimensional, focusing only on temperature variations along the z axis. In reality, radial temperature gradients can exist, especially near the reactor wall, but for many cases, the one dimensional approximation provides a good starting point. Here we see a general expression for the axial temperature gradient, while presented in slightly different form later from each zone. This equation introduces key parameters such as the effective thermal conductivity and the superficial fluid velocity and the fluid density, the heat capacity of the fluid HCP, and the heat generated by the reaction per unit volume S. The effective thermal conductivity Ke is not simply the thermal conductivity of the fluid but accounts for heat transfer through both the fluid and the solid particles in the packed bed, as well as the mixing and dispersion effects within the bed. It is a crucial parameter that can vary between the inert and the catalytic zones due to the potential differences in packing and flow characteristics. Now we will present zone specific second order ordinary differential equations for temperature as a function of Z. For zone 1, this equation describes the temperature profile. Notice it's a homogeneous second order equation, meaning there is no source state present, reflecting the absence of the primary chemical reaction. The heat transfer in this zone is primarily governed by axial conduction, that is represented by the term involving the second derivative of the temperature with respect to z, and convective heat transfer, that is represented by the term involving the first derivative and the fluid flow. Now for zone 2, this equation is the governing equation. This equation is non-homogeneous due to presence of the term S, which represents the chemical heat source or sink. The form of S itself can be complex, often being as a function of temperature and the concentration of reactants, as dictated by the reaction kinetics. The nature of S significantly affects the complexity of the solving this differential equation. And for zone 3, where z greater than L, we got this equation, and this equation again describes a region without the primary chemical reaction, and thus the equation is similar in form to that of zone 1, involving axial conduction and convection but without the S term. The fact that these are second order differential equations implies that their general solutions will contain two arbitrary constants of integration for each zone. To determine these constants and obtain a unique solution that describes the temperature profile throughout the entire reactor, we need to apply appropriate boundary conditions. This leads us to the more in-depth discussion of boundary conditions. As we touched upon earlier, these conditions provide essential information about the state of the system at specific locations, typically at the boundaries or interfaces of our defined regions. They are crucial links between the general mathematical solutions of our differential equations and the specific physical reality of our reactor. Without approximate boundary conditions, we would have an infinite number of mathematical solutions, none of which would necessarily correspond to the actual temperature distribution in our reactor. For our three zone reactor system, we need to consider the conditions at the inlet, the outlet, and the interfaces between the zones. Our sources provide a detailed set of these boundary conditions. Boundary condition 1, at the inlet zone of 1, where Z tends to minus infinity. The temperature T approaches the feed temperature T naught. The assumption of extending zone 1 to negative infinity is a mathematical idealization. In practice, it implies a region sufficiently upstream where the influence of the reaction zone is negligible and the fluid has reached a steady inlet temperature. This condition helps us to fix one of the integration constant that will arise from solving the differential equation for zone 1. Now boundary conditions 2 and 3. At the interface between zone 1 and zone 2 where z equals to 0, here we have two crucial conditions that ensure physical continuity at the boundary between the inert and the catalytic sections. That continuity of temperature. The temperature just before the interface in zone 1 must be equal to the temperature just after the interface in zone 2. That is T equals to at t z equals to 0 minus and at t z equals to 0 plus. This is a fundamental requirement based on the principle that temperature should be a continuous property in a continuous medium. Abrupt temperature jumps at an interface would violate the laws of thermodynamics under these conditions. And now, continuity of heat flux. The rate at which heat is being conducted towards the interface from zone 1 must be equal to the rate at which heat is being conducted away from the interface into zone 2. In the equation is as follows. The negative sign arises from the convention that heat flux is positive in the direction of decreasing temperature. Here K and K effectiveness in zone 2 represent the effective thermal conductivities in zone 1 and zone 2 respectively. It's important to note that these effective thermal conductivities might be different due to differences in the packing material, inert versus catalytic, and potentially different flow characteristics. This condition ensures that energy is conserved at the interface. No heat energy is instantaneously accumulated or lost at this boundary condition. And now boundary condition 4 and 5. At the interface between zone 2 and zone 3, that is at z equals to L, similar to the first interface, we again have continuity of temperature and heat flux. Now we will discuss about continuity of temperature. T at z equals to L negative is equals to T at z equals to L positive. The temperature must be continuous as the fluid moves from the catalytic zone to the exit zone. Now continuity of heat flux, and the equation is as follows. Again, this ensures energy conservation at the interface between the catalytic and inert packing of the exit zone. K effective in third zone represents the effective thermal conductivity in zone 3, and which might be the different from KE1 and KE2 depending on the packing and flow conditions in this final zone. And now boundary condition 6. At the outlet of zone 3, that is Z tending to positive infinity, the temperature gradient approaches 0. Similar to the inlet condition, the assumption of an infinitely long exit zone is a mathematical simplification. This condition implies that far downstream from the reaction zone, the temperature profile becomes flat, indicating that there is no further net heat transfer in the axial direction. This often occurs when the fluid has reached thermal equilibrium with its surroundings or when axial conduction becomes negligible compared to the bulk flow of heat. This is a type of zero gradient boundary condition. In total, we have 6 boundary conditions. This is precisely the number of conditions required to solve our system of 3 second order differential equations. As each second order equations yields 2 constant of integration, resulting in a total of 6 unknowns that need to be determined. Now let's delve deeper into the process of how we actually utilize these boundary conditions to obtain the specific solution for the temperature profile in each of the 3 zones. The general methodology involves a series of interconnected steps. Here,